BIO552. Today we are going to present about an experiment where we have to determine the concentration of an unknown sample of iron trichloride. But before we dive deeper about the procedure of this experiment, we have to know the importance of using spectrophotometer to conduct this experiment. The reason why this experiment uses spectrophotometer is because it can measure the amount of light transmitted by a substance by measuring the intensity of light as a beam of light passes through the solution. As for this experiment, the solution that was used is iron trichloride. Next, what is the principle that was used while conducting the experiment? It is called transmittance. So, what is transmittance? Transmittance is the relative amount of light that passes through the sample. This can be calculated using a formula where IT is divided by IO. Bear in mind that in order to calculate the absorbance, we're going to use percent transmittance, where we just need to multiply the value of transmittance we got with 100. Moving on to the instrumentation involved in the spectrophotometer that was used in this experiment. It consists of light source, monochromator, sample, cuvette, detector, and digital display for value reading. In spectrophotometric methods, the detector measures the amount of light being transmitted by the sample. In order to have a better understanding about the experiment, a few things were identified. Firstly, the problem statement of this experiment is how the concentration of an unknown sample of the solution is determined. Next, the aim or objective of this experiment is to determine the concentration of an unknown sample of iron trichloride. Next, the hypothesis for this experiment is if the procedure is performed accordingly, it will give the simultaneous analysis and the concentration of an unknown sample in iron trichloride can be determined. There are several materials and apparatus that were used in this experiment. It includes passive pipette, 0.4 molar of iron trichloride, test tube rack, graduated measuring cylinder, deionized water to make dilutions, cuvette to place the sample, and UV VIS spectrophotometer to measure the key value for this experiment, which is the transmittance of the sample for each dilution.
This experiment uses spectrophotometry and applies Beer's law to determine the concentration of an unknown sample of iron trichloride. The apparatus and materials were set up including a stock solution of 0.4 molar iron trichloride and an iron trichloride solution with unknown concentration. To prepare a 1/10 dilution of iron trichloride, 1 ml of stock solution of 0.4 molar iron trichloride was pipetted into a 10 ml measuring cylinder. Then 9 ml of distilled water was added into the same measuring cylinder to dilute the solution. Then the solution was transferred into a test tube. The solution was stirred to mix them well. 5 dilutions were created to give samples of 0.04, 0.08, 0.2, 0.32, and 0.4 molar of iron trichloride. The unknown sample of iron trichloride was pipetted into a cuvette until 3/4 cuvette was filled. Visual comparison of unknown sample with known solution was made to see which of the samples is the unknown solution most similar to. Unknown sample's concentration was seen to have a concentration between the two dilutions, which are 0.08 and 0.2 molar of iron trichloride.
The spectrophotometer was turned on at least 15 minutes before the experiment is started. The cuvettes and test tube need to be cleaned first by using the deionized water. Basically, cuvettes are made by quartz since function as UV visible in spectrophotometer. Handle them with care to prevent any damage. The cuvettes are wiped with Kim wipe to prevent any scratching of the glass that will disturb the results of the experiment. Spectrophotometers are also calibrated by using a blank solution that we prepare containing all of the components of the solution to be analyzed. The blank solution in this experiment is a deionized water. Blank solution acts as control that contains the chemical solvent in which the solid is being analyzed and dissolved in. This is because the water and the cuvette also absorb light, so the spectrophotometer will not measure the water and light absorptions. Next, before the experiment starts, the wavelength should be set to analyze the sample. In this experiment, the wavelength has been set for 625 nanometers. After that, the value of transmittance will be measured for each tube. Next, the transmittance is going to be found by dividing the transmitted light or the output by the incident light, which was the input. This varies as a function of the sample concentration using the transmittance. The absorbance was calculated using the equation that is equal to the negative log of the transmittance. The percentage value of the transmittance needs to be converted in a decimal form first. In this experiment, the transmittance for the one-third dilution worked out to be 97.1%. Next, the one-fifth dilution was 96.3%. The one-half dilution sample had a percent of transmittance of 90.3%. The 5/5 dilution sample had an 83.8% of transmittance, and the 0.4 stock solution had a transmittance of 80.6%. Lastly, the unknown A have a transmittance of 91.5%. So all this information about the transmittance will be used to find the absorbance that is important in implementing the BIO's law principle.
With transmittance result, we can then calculate absorbance of each samples by using equation of absorbance equals to negative log of transmittance. Decimal form of percentage transmittance is used in order to calculate absorbance. The results obtained are as shown in the video. Now that we have obtained absorbance result, we can continue to make BIO's law plot graph in which absorbance on y-axis plotted against concentration on x-axis. Once all the point is plotted, it is common to feed a trend line with equation of trend line and r-squared value. When all samples with known concentration and absorbance are done plotted, we can now work on unknown sample with spectrophotometer to measure their transmittance, and absorbance is calculated. By using the same equation, absorbance equals to negative log of transmittance, we will then obtain the result of 91.5% of transmittance and 0.0386 of absorbance. BIO's law states that there is a linear relationship between the concentration and the absorbance of the solution, which enables the concentration of a solution to be calculated by measuring its absorbance. BIO's law comes with a relationship between concentration and absorbance given by equation A equals to epsilon Cl, in which A is absorbance, epsilon is the molar attenuation coefficient, C is the concentration, and L is the path length. Path length is 1 cm, which will not go into factor in calculation. BIO's law equation is actually correspond to best fit or trendline equation y equals to mx plus b. The slope m is equal to epsilon L. Hence, by using the result of linear regression analysis, we will be using trendline equation to determine the x or concentration of unknown sample. From the graph, we need to find the intersection of concentration and absorbance for prediction before doing calculation. With 0.0386 absorbance, a horizontal line is drawn to where it is intersects at trend line and drop down to x-axis, which is the concentration. It can be estimated that the concentration of unknown samples lies in between 0.16 molar to 0.17 molar. The equation is rearranged and resulting concentration, or x, equals to y minus b divided by m. The calculation will be as shown in the video. Absorbance of unknown sample 0.0386 minus with b 0.0002 and then divided by slope m 0.2337. The answer will be 0.172 molar of iron trichloride, which agree with the prediction from graph intersection that we did earlier.
Next part is about the scientific explanations of the experiment chosen. You guys might wondering, why do we need 5 dilutions to perform this experiment, right? These dilutions are needed to assist in determining the concentrations of the unknown sample by plotting the data of the amount of absorbance and the amount of concentrations of the solution in the graph to achieve the calibration line. The calculations of concentration is governed by the Lambert-Beer law. Once the calibration line is established, by having the standard curve, the unknown concentrations of the sample can be determined by plotting in the above graph. In this experiment, the spectrophotometer was calibrated by testing it with the deionized water. Stated in the video, the transmittance of the DI water must indicate 100% in the order for the spectrophotometer to functioning. 100% transmittance means that there is no light of that wavelength is absorbed by the blank solution. It is important to blank the spectrophotometer before taking an absorption measurement of a sample at each new wavelength, because the water and the cuvette also absorb light. So the spectrophotometer will measure the absorptions of water and the cuvette. Just as you clear the number on the calculator, calibrating a spectrophotometer ensures that the spectrophotometer is set to 0. Potential issues and errors are also corrected during the calibration. Wavelength of maximum absorbance is used when determining the concentration of a color solution, since at this wavelength, a slight change in concentrations allow for a significant change in the absorbance of light. The higher the absorptions of the wavelength provide high sensitivity. The wavelength selection is important and depends on the color of the suspension medium. The wavelength range that exhibits the greatest absorbance is 600 to 670 nanometer, which correspond to the color orange and the little red, the same as the color of the sample, which is iron 3 chloride. Based on the data in the table obtained from the experiment, the higher the dilution made, the lower the transmittance of the solution will be. The higher the dilution means that the color intensity of the solution is higher. There will be less light transmitted and more light will be absorbed if the sample is darker. The proportion of the light absorbed will depend on how many molecules it interacts with. Suppose you have got a strongly colored organic dye. If it is in a reasonably concentrated solution, it will have a very high absorbance because there are lots of molecules to interact with the light that cause the amounts of the light transmitted become less. Graph absorbance versus concentration shows the linear relationship, which is if the higher the concentration, the higher the absorbance will be. In linear plotted graph, the equation y equal to mx plus c can be used to obtain the data from the graph for calculations. The best fit line of the linear equation was created, which is here. The R2 value is near 1, which is 0.9948, represent that the values are close to the actual linearity to the data. In this experiment, the concentration of the unknown sample obtained from the graph is predicted to be 0.16 molar to 0.7 molar. That means the point for the unknown concentration lies under the standard curve between the dilution 1/5 and 1/2. The result from the comparison and the graph came out clearly as it should be. Using the Beer-Lambert law equation, the value of the unknown concentration is calculated to be 0.172 molar, which is still in the range of 0.16 molar to 0.17 molar. The prediction made is agreed with the answer of the calculation. According to this experiment, the higher the concentration of solution, the higher the amount of the absorbance. However, the higher the amount of the absorbance will result in the lower amount of the transmittance. In conclusion, the relationship between the absorbance and the concentration is linear. The spectrophotometry assists in finding the transmittance of each dilution. The concentration of the other sample using the Beer-Lambert law equation is tallied with the prediction from the standard curve, which is 0.172 molar.